The goal of exercise 2 is to continue exploring the orthogonality between the residuals and the predicted data values. Now, the predicted data values from a model is just one way of combining the columns of the design matrix. So it's one linear combination of all the columns of the design matrix. Now, on the one hand, that is a particularly good linear combination of all the columns. In fact, it is the best combination of the columns if the goal is to account for as much of the variability of the data as possible. So this linear weighted combination is not some random weighting. It is the best weighting to minimize the errors of the prediction of the real data. But the idea that we are going to explore in this exercise is that the predicted data is just one of an infinite number of ways of linearly combining the columns of the design matrix. And so that means that the residuals vector is not just orthogonal to that one specific unique combination. Instead, the residuals vector is orthogonal to the entire subspace spanned by the design matrix. So your goal in this exercise is to figure out a way to demonstrate that that is the case in Python. And my hint here is to think about the left null space of a matrix, the design matrix, and the rank. And you might remember that I showed you an algorithm for determining whether a vector is in the column space spanned by a matrix. So a couple of hints there. I hope that helps you figure out how to solve this. I will first talk about the solution a little bit here, and then I'll switch to Python and I'll show you what my solution looks like. And I certainly don't mean to imply that it's the only coding solution. Okay, so here's the idea. If the residuals vector is orthogonal to the entire design matrix, then that means that the residuals vector is in the null space of the design matrix. So what I am going to do in Python is calculate the null space of the matrix and then use the augment and rank technique that I introduced earlier in the book to evaluate whether the residuals vector is inside the column space of the null space of the design matrix, in particular the left null space. Okay, I hope that makes sense. If what I'm saying sounds weird or you don't follow, or you don't understand, I'll explain it a little bit more when I show you the code. But basically, it also means that you should go back and review earlier parts in the book where I talked about the left null space of a matrix and using the rank algorithm to determine whether a vector is in the column space of a matrix. So here I have a little bit of text in the comments. It's basically just explaining what I just explained. And actually, let me start by just running this line here. So this gets the left null space of the design matrix. So now I'm just going to print this out so we can have a look at it. Okay, so this is a bunch of numbers. Maybe that's not that helpful. Okay, then let's look at the shape. So we see that the shape of the left null space is 20 by 18. And what does that mean? Actually, let me do something else. I'm going to print out the shape of x transpose x. Okay, x dot shape like this. Okay, so x is our design matrix. That is 20 by 2. So we have 20 data points, 20 observations, and we have two features, that is an intercept and the number of courses taken. Okay, so this is the design matrix. Now, it has a null space that is that can be represented as a 20 by 18 matrix. So 20 corresponding to the number of rows, and 18 because this basically has to flesh out the rest of the RM, the rest of the ambient space in which this matrix is embedded. And so these two columns form a linearly independent set. The rank of the design matrix is 2, and so therefore the null space, the dimensionality of the null space needs to be 18. Okay, I hope that makes sense. And now what I'm going to do is uncomment these. I think I'll just undo all of this stuff. Okay, so here what I do is augment the residuals vector onto the null space. Now you have to do a little bit of trickery in Python here because this vector here, res, actually doesn't have any intrinsic orientation. So we need to endow this vector with an orientation, turn it into a column vector. So we can then horizontally stack this vector next to this matrix, and that gives us the augmented matrix. And then what I do is compute the rank of the null space matrix and the null space matrix augmented by the residual. Now, as a reminder, if these two matrices have the same rank, it means that the residuals vector, this augmented vector, is not contributing any new information. Everything that is in this residuals vector is some linear, or can be expressed as some linear combination of the columns in this matrix. However, if the rank increases, so if the rank of this matrix is higher than the rank of this matrix, for example, if this is rank 19 and this is rank 18, then that means that this residuals vector cannot be expressed as any combination of these columns, which means it is a unique vector. It means it is not contained in the column space of this matrix, which means it's not in the null space of this matrix, X here. Okay, so a lot of explanation, but here we see, but I hope that, everything I just said is a reminder to you and not new information. Okay, so we see they both have the same rank of 18. That means that the residuals vector is in the null space of the design matrix, and that means that the residuals vector is not only orthogonal to the one very specific linear combination of all the columns that produces the predicted data. Instead, the residuals vector is orthogonal to the entire column space of the design matrix.